Hi, let's see how we can use Bayes' theorem, probability theory, and a tree diagram approach to solving Bayes analysis. So let's say that we have a product that we know is 1% defective, so the probability of defect is 1.01. And we also have a diagnostic test to see whether or not this product that comes off of the manufacturing line is defective or not. But these diagnostic tests generally could be not very effective. And so let's say that the probability that given that the product is defective and the test will show that it is defective equals 0.94. We also know that probability that given that an item is not defective, but the test will show that it is defective equals 0.02. Now we want to find out what is the probability that the test shows a defective item, and what is the probability that given that the test shows the item is defective, the item is actually defective. So these two are the two questions that we would like to answer. So of course, to use formulas, we know that this equals the probability of test being defective is the probability of item being defective given that test says defective, plus the probability that the item is not defective and the test says the item is defective. So these two joint probabilities, the summation of them would be the answer to the first question. This one is a conditional probability. So using the Bayes formula, we can write that or answer it by computing the probability of defective item and test showing a defective item divided by probability of the test being defective. So this is how we can solve these two problems. But I will show you with a tree diagram approach how to solve not only these questions but also many others. So with this tree approach, we start the analysis with two sets of branches representing the variable for which we have a simple probability. Now here we have a simple probability given to us, and that's probability of defect being the item being defective as 0.01. So I'm going to mark this as this set of branches as being actual result, and that's being the item being defective or item being not defective. Now we know that probability is 0.01, so this one will have to be 0.99 because these two must be exhaustive, mutually exclusive and exhaustive. Now I will branch it off and record here the results of test results on the second set of branches. And that is the test result could be either test says defective or test says not defective. But these would be conditional probabilities. Condition being met is that the item was in fact defective, right? So I'm going to put that here. This branch will have a probability of test being defective given that the item is defective, and this is test being not defective, test saying not defective, given that, let me correct that right there. This is test being not being defect, saying that the item is not defective given that the item is defective. And over here, the same thing. This is test says item is defective, or test says item is not defective. But this is given that the item in fact is not defective, because these branches right here, they stem off of this one, which shows the item is not defective. Okay, so these probabilities we do have. These ones, test being conditional probability of TD given D. TD given D is this one, so 0.94. And if that's 0.94, then this has to be 0.06, because these two branches must add up to 1. And this one is TD given D bar, which is 0.02, so this has to be 0.98. So again, because these have to be complements to each other. Okay, so notice that these are simple probabilities or marginal probabilities, and these are conditional probabilities. And if I multiply the simple by the condition, its associated conditional, the answer are joint probabilities. Okay, so over here I'm going to have the probability of D and TD. D and TD. This one is probability of D and TD bar. D and TD bar. This one is probability of D bar and TD. And this is probability of D bar and TD bar. Okay? And so simple times conditional equals joint. So 0.01 times 0.94 is 0.0094. This one is 0.01 times 0.06, so it's 0.0006. This is 0.99 times 0.02, so the answer is 0.0198. And this one is 0.99 times 0.98, which is 0.9702. Okay, so we have created our first set of branches, and now if we already we have enough information to answer this first question, question number 1. Question number 1, and this is question number 2. Question number 1 says, what is the probability that the test would give, would say that the item is defective in general? So that is probability of D, joint probability of D and TD, and D bar and TD. So we already have that. D and TD is right here. D bar and TD is here. So the joint, or the summation of these two numbers, would be the answer. So this would be question 1 is 0.0094 plus 0.0198. 94, yeah, and that is 0.0292. 0.0292. But I will go ahead and do what's called flipping of the tree, and we can answer all kinds of other questions as well. So we have, we started out our tree but with the actual results. Now we're going to start the tree with the test results. So that's test saying defective, test saying not defective, and then the other event is actual test result or actual results, meaning item is defective or not defective. Item is defective or not defective. But again, remember these are conditional probabilities. Given these two would be given TD, and these would be given TD bar. Okay? And then, of course, these are the joint probabilities. These orders are going to change. So here we have TD, and this is TD and and D. D and TD. These are the two events that are on the top branch. This one is TD and D bar. Next one is TD bar and D. Last one is TD bar and D bar. Okay, let's find these. These are all probabilities. These are all probabilities. Let's find these from this first diagram. So TD and D was here, and that's 0.0094. This next one is TD and D bar. TD and D bar. It's this one with the red star next to it, 0.0198. Next one is TD bar and D. TD bar and D. That's this one, 0.0006. And the next one is the last one, 0.9702. Now you can see very easily that this number and this number both end up going where? They both end up to here. So that's why the summation of these two numbers was 0.0292, 0.0292, which we answered right here. Okay, so the difference between that and 1 is going to be 0.9708, 0.9708, because these two probabilities must add up to 1. Or if I sum up this number and this number, it will add up to 0.9708. All right, now the last set is computing question 2, which is this one right here. This right here is the probability of D and TD, D and TD, which is 0.0094, divided by probability of TD, which we computed to be 0.0292, 0.0292. And that answer is 0.3219, 0.3219, 0.3219. So this is, I'm going to erase this so that it's not in the way. Okay, so 0.3219 is the answer to question 2. And the answer to question 1 was 0.0094 plus 0.0198, which we found out to be 0.0292. 0.0292. Now over here you can see that we computed 0.3219, but from the tree, remember again we still have this relationship, simple times conditional equals joint. So if we have the joint and if we have the conditional, if you have the joint and if you have the simple, then all we have to do is divide the joint by the conditional, by the simple probability to get the joint, which is 0.3219. So similarly, we can do all of these 0.0198 divided by 0.0292 is 0.6781. 0.6781. Of course, we could have subtracted this number, 0.3219, from 1 to get this. Similarly, 0.0006 divided by 0.9708 equals 0.0006. It just happens to be that number. No, just that's how the numbers turn out. And so subtract that from 1 and you get 0.9994, or another way is to divide 0.9702, the joint, divided by the simple 0.9708 to get the conditional, which is 0.9994. So I hope this helps you relate simple, conditional, and joint probabilities together and be able to use Bayes' theorem formula using a tree diagram approach so that you can see where all the numbers are coming from. Okay, thank you.